Okay, we are talking about CHAID analysis today. CHAID stands for Chi-Square Automatic Interaction Detection. It is a statistical analysis that's used for prediction and classification models that is easily explainable to many audiences. From what I've read, a lot of marketing people use it. So it's decision trees in general, which CHAID is a type of one. They're easy to understand, they're useful in data exploration, they don't require much data cleaning, and typically the type of data is not a constraint for them, and they're also a non-parametric method. They do have a couple disadvantages of sometimes they overfit the model and they're not suited for continuous variables. So the statistical procedure of CHAID is very robust. It makes no assumptions about the data's distribution or normality. It's based on the chi-square test, as I said, and it helps one to be able to tell a story about their data. It allows for us to find the most useful predictors of an outcome, and the algorithm does this by parsing a predictor variable into the most distinct subgroups with respect to the dependent variable. So this also is done while preserving for parsimony and adjusting for type 1 error. So basically what it does is it uses the Pearson's chi-square test of independence to test for an association between the two categorical variables. And so if it's statistically significant, it indicates that the two variables are not independent, aka they have a relationship between them. And so what it's looking at is it's looking at all of your independent variables to see what is the biggest predictor of the dependent variable, and there can be interactions that actually predict. And it breaks them down into the smaller groups. And so CHAID analysis are actually better to do with a larger sample size because they're more reliable in that sense. You have more people, so they're able to make a better prediction as to whether or not that IV is actually going to predict the DV. So the CHAID library in R requires any variables entered as predictors to be either nominal or null. I was first looking at attrition, so whether or not the employees stayed or left the company, and this would have been easier to interpret than what I actually ended up running, but it did not. Since I made up the data, I didn't find anything statistically significant. I actually had to look at marital status. It was broken into 4 different categories, which made it more difficult to understand, but typically CHAID is used to say, like, this type of person is more likely to leave the company or this person is not. And so someone would be able to use that data to say, okay, well, what should we look for in an employee? If they are on salary, they're under 25, and they graduated from college, and they're single, then maybe we should focus on that group since they're more likely to leave than the rest of the organization. So looking at my factors, right here is my data. I had attrition, so that was yes, they say at the company if it was a 1, or no, they left if it was a 2. Age was 1 for if they were 50 and under, or 2 if they're 51 and above. Education level, 1 is high school degree, 2 is an undergrad degree, 3 is those who finished graduate school. Gender was 1 for female, 2 for male. And performance rating was 1 for low performance, 2 for average performance, and 3 for high. And payment type had 2 categories. 1 was hourly payment, and 2 was salary. And then marital status is 1 for single, 2 for divorced, 3 for married, and 4 for widowed. And these are just categorical. The numbers don't mean that like 2 is better than 1 or greater than 1. Okay, now we're going to talk about how I ran this statistic. So I attached the data set called Help Me. I installed the packages, so the CHAID package, the party kit, the grid, the libcoin, and the MVT norm. Those are all new packages we haven't used in R before, and they had to be installed before I could run the statistical analysis. I also libraried them as well so that I would have them. I then did a summary of the data, which was just to make sure that it was connected correctly. I then had to create factors, which you can see. Well, I'll show you, I guess. You can see them somewhere. I created factors here so that R would be able to know what factors I was talking about that I was putting into my CHAID analysis. Right here is where I check just to make sure that everything actually ran as a factor. And you see true after all of these, so they were created as factors. And for instance, attrition turned to ATT, age became AG, pretty straightforward, education level EL. So now we're actually getting into what I actually did to run the CHAID. So first I did a control. I created the control right there, which is just setting the parameters of the model. The min split, which is right here, equals 2, represents the number of observations in splitted response at which no further split is desired. So if a variable meets all of the criteria for a split, but it has less than 2 people, then the split will not be performed. So that was my minimum number of people that had to be required for the split to happen. The min bucket is the minimum number of observations in the terminal modes, which was also set at 2. The alpha 2 at 0.05 represents the significance levels desired. So alpha 2 is the threshold p-value at which groups will be merged if the observed p-value for a test of their difference is larger than 0.05. But alpha 4 actually is something different. It's also set at 0.05, by the way. And it is the threshold p-value at which the groups will be split, not merged, if the observed p-value is smaller than the threshold. And I set both of these at 0.05, so the groups would be merged if it's larger than 0.05 and split if it is below 0.05 or statistically significant. So that's what the controls are. They just tell R how to split my decision tree. So then I'm actually going to create the model for my decision tree, which I called CHAD-MAR, so marital status. As you can see, CHAID is the analysis I'm running. MAR-STAT actually represents the DV, so that is my dependent variable that I'm trying to see what predicts it best. And then we have all these other ones: performance rating, education level, gender, pay, attrition, age. This is the data set is help me, and we're using the parameter set and that control above. I could have done a tilde and then a period, comma, which would have encompassed all of these IVs, but as I said, I was trying to look at attrition first and it didn't work, so I tried every single IV until I actually got a decision tree to come out. So now if I'm going to press, I've run all of it, I'm pressing print. That's actually going to give me the information right here. So the model formula, MAR-STAT was the model I ran, and that is looking at the marital status. That's the DV, and these are the IVs. And as you can see is we have the root, which is the top of the tree, and everything comes from the root. So we have 2 inner nodes right here and right here, and we have 3 terminal nodes right here, and right here. So terminal nodes actually mean that it cannot be broken down any farther. That is as far as it can go to still be predictive of the DV. So CHAID selects a predictor that has the smallest adjusted p-value, aka the most significant predictor. So in this case, it's actually age right here, which is the root node. The p-value is less than or equal to what I specified in alpha level 4, so 0.05, and so therefore the node was split using the predictor. It is a terminal node for employees under 51, so those right here, but it's actually not a terminal node for those above 51 and above right here. As far as looking at the right side of the tree, so those 51 and above, attrition right here is actually an internal node. So here's an internal, which then connects them to the terminal node right here and right here. So the very bottom is terminal nodes, the middle is internal, and the top is roots. This means that splitting the data farther than past attrition did not yield insignificant results for predicting marital status. So at this first level of the trunk, we have all employees, which was 250. Age had the greatest impact on the likelihood of a particular marital status. It was the most predictive. So 128 employees are 50 and below, while 122 are 51 and above, as you can see with these ends right here. For those 50 and below, they are most likely to be single, which is number 1, followed by most likely to be widowed, then divorced, then married. But that's not the same for these, and you're able to tell that by where the 1, 2, 3, and 4 of the categories of marital status line up over here on this left side with the numbers. For those 51 and above, attrition also interacts to help predict the employee's marital status. So those who are 51 and above and are still at the company, they are most likely to be divorced, as you can see right here. For those who are 51 and above and have left the company, they are most likely, noticeably, to a higher extent than in these other cases. So this is where we're looking right here. They are most likely to be married, and they are not very likely to be single. So none of the other predictors significantly predicted the marital status of the employees. So once again, age, if you're 50 and below, you're going straight to marital status. But if you're 51 and above, your attrition is also influencing the prediction of your marital status. So next I ran the simple chart as you'll see right now, it just gives the numbers in a different way, and it's easier to understand the erroneous values. So when we look at the simple chart, we see that for employees who are 50 and below, over here, we predict that they are most likely single, but we could be wrong 70.3% of the time. So that means that while the highest percentage of the employees of the organization below the age of 51 are single, we're not able to predict that every employee 51 and below will be. And hopefully if you're actually using this in a real organization, you're going to have a much lower error rate. As for employees 51 and above, we see that those who are above and have also stayed at the company, they're most likely divorced, but we're wrong 68.2% of the time. So once again, we're not able to predict that every employee who's at the company and 51 and above is actually divorced. And as for those who are 51 and have left the company, we predict that they are most likely married, but we are wrong 40% of the time. So while our prediction is stronger in this case, we're still wrong almost half of the time. So my data and my decision tree is not something you should ever make an organizational decision off of. But decision trees are good for breaking large data sets into smaller predictive elements, and they also allow us to make sense of the data and tell a story to a client. Alrighty, goodbye.